Thank you for joining us and welcome to Stantec Water webinar series. We are pleased to present a panel of Stantec PFAS professionals and subject matter expert Chris Moody from AWWA. Today we are speaking on the impacts of the new PFAS maximum contaminant levels in drinking water. I am Heather Dean, your hostess. During this meeting, you will be in listen-only mode. We invite you to submit questions at any time during the presentation. If you're joining via computer, you can do so by expanding the questions box in the side panel of your screen. If you are on a mobile device, click the question mark located at the top of your screen. Your questions will be addressed following the presentation. And with that, I will hand it over to Nicole Boulay, Stantec's Water Treatment Sector Leader, to get us started.
Thank you, Heather. As Heather mentioned, our topic today for our webinar is there is a proposed PFAS maximum contaminant level for drinking water. What do I do about it? This is a pretty hot topic in our industry today. And Stantec has several projects that we're working on, and we're hoping to share those lessons learned with you as part of this webinar. And Chris Moody from AWWA, we're very happy to have him as a special guest speaker today. So our speakers are listed here on this slide. My name is Nicole Boulay. I am the North American Water Treatment Sector Leader for Stantec, and I sit in our Fairfax, Virginia office. Chris Moody, as I mentioned, is here from AWWA. He's their Regulatory Technical Manager and a PFAS subject matter expert for AWWA. Katie Chamberlain is out of our Burlington, Massachusetts office. She's a Senior Associate and a Water Treatment Regional Practice Leader. Ryan Capel is out of Minneapolis, Minnesota, and he's a Water Treatment Lead, and he also leads our PFAS focus group here at Stantec. And Kim Pugel is out of our Bellevue, Washington office, and she is a water policy and funding specialist. I also want to point out that Dr. Joe Jackangelo is also participating in the webinar today and will be available for answering questions. We're giving him a little break on speaker duties today, but he is our Director of Research and also serves as the President of AWWA. And he also leads our Johns Hopkins Stantec Alliance, where we do PFAS analysis and studies. And as I mentioned, he's happy to answer any questions at the end of the webinar. So our agenda today is I'll be providing some introductory remarks. Chris will then speak about the PFAS regulatory outlook for drinking water. Katie Chamberlain is going to talk about where do you start if your PFAS levels are above the regulatory levels. And these, again, are proposed levels. And then Ryan Capel is going to talk about an approach to piloting and why you should consider piloting. And Kim Pugel will finish out on funding considerations, and we're hoping to have 10 to 15 minutes to talk about questions and answers. So what are per and polyfluorinated alkyl substances, or PFAS? Well, these compounds were initially manufactured beginning in the 1940s, so they've been around a long time. Characteristically, they have a very strong carbon-fluorine bond, which is partly why it's difficult to treat them and to destroy them. Some of the other characteristics are that PFAS are neutral and ionic, they have thermal and chemical stability, and they have stain repellency and surfactant behavior, which makes them attractive to manufacturers. It's estimated that there's been over 10,000 compounds, PFAS compounds, released in the environment. I've seen numbers up to 14,000. And once they're in the environment, they're persistent and ubiquitous. And of course, PFAS compounds are of increasing health concern all around the world. So there are many sources of PFAS, and this slide just lists some of the industries that use PFAS in their manufacturing. For example, in electronics, PFAS can be found in computer parts. In firefighting foam, I'm sure you've heard of the AFFF foam that's used and it's very effective on jet fuel. And then household products, things like nonstick pans, dental floss, makeup, they all have PFAS in them. So it's really quite prevalent, and then a lot of times what goes into manufacturing ends up in our source waters and our drinking water plants. So I'm going to turn it over now to Chris Moody to give a regulatory outlook on PFAS.
Thanks, Nicole. So everyone's probably pretty aware of the fact that the proposed regulation came out not last month now, but the month before that in March, just before I went on vacation. So that was great timing. But there's been a lot of other federal actions recently that are worth taking note of, and they're all kind of playing together as we move through the process. So we have the Protecting Drinking Water through the Safe Drinking Water Act actions, but then we've got data reporting requirements so we better understand where they're coming from, where they're at, what the prevalence is. And then we have curbing wastewater releases and curbing releases through biosolids that are moving through. The third one there is really more about the industrial side of things, ELGs, pretreatment programs, but curbing releases through biosolids can be focused more on, municipal biosolids so that we better understand what the land application can look like. And then we have addressing legacy pollution, and really the big one there is CERCLA, and that's a long acronym, but really the short term for it is Superfund. It's the better way of saying it. Everyone really recognizes it. It's all about getting contaminated sites cleaned up by creating liability, and we'll talk a little bit more about that just before I cut off later. So if we start to think about addressing PFAS in drinking water supplies, we get into a really odd spot for Safe Drinking Water Act because it tends to be a pretty linear process where you run through this series of checklists and basically you work your way through the rule to come up with new rules and do reviews. So in short, you have the CCL, which is the contaminant candidate list. That's more about prioritizing potential contaminants that aren't currently regulated and better understanding what the research needs are. UCMR is all about the unregulated contaminant monitoring rule, and that's where you start monitoring for a certain amount of compounds in drinking water over the course of 3 years at the same time so that we have a national perspective on what occurrence looks like in drinking water for different contaminants. And then the regulatory determinations is what we saw a couple of years ago for PFAS, and that's more about, you have some data that suggests maybe this is worth addressing. And so it's a determination to take a regulatory route and determine what a proposed rule might need to be. And then they actually do a proposed rule and finalize it. And then that last item there is a 6-year review, which probably is the less spoken of part of Safe Drinking Water Act, but that's where every 6 years we come in and we say, are the existing regulations protective enough for public health, or can they be improved because either analytical methods have improved, new research has come out that says that they're more toxic than we thought, or there's more occurrence than we thought, something like that. So if we start to think about PFAS in this diagram, it's really interesting because usually contaminants just kind of plop their way through. For PFAS, we are in CCL. We have a final CCL 5 that was just recently finalized last year, and that contains some number of PFAS from, we know it's more than 1,300. We don't know if it's 9,000 or, now there's this number that Nicole just mentioned about 15,000. So there's a big question mark really on the end of that spectrum. And then we have UCMR 5 that we're all probably aware is currently undergoing, that process for the next 3 years, and that's 29 different PFAS, which was directed by Congress. And then if we work over to the recent action, we have both regulatory determinations and a rule that was proposed. The regulatory determinations that are being made in this rule are for 2 long chain compounds, perfluorohexane sulfonic acid and perfluorononanoic acid, so PFNA, PFHXS, and then 2 short chain or more commonly referred to as replacement compounds, PFBS and GenX, or perfluorobutane sulfonic acid. And GenX is, the other way of saying it is HFPO-DA, or hexafluoropropylene oxide dimer acid. Try not to say that 3 times fast, but those are 2 replacement compounds. And so they've made determinations for those 4, and then they've proposed the rule along with PFO and PFAS. And then I have that big question mark at the end because, a lot of the ways that this is being proposed feels like putting the path out in front of us to come back in a 6-year review and add additional compounds. If we go to the next slide, we'll see what those standards actually look like. And so we've got 6 different standards and MCLGs have been proposed, but really it's only 3. And that's because for PFO and PFAS, we've got a cancer determination for those 2. So the MCLG pretty much standard goes down to 0 PPT. And then the MCLs, based on kind of a practical quantification limit that they've determined, are set to 4.0 because they essentially are saying that they think there's merit in going to 4.0 and essentially having non-detect be the goal. The third one there is the hazard index of 1.0, which is both an MCLG and an MCL. and that's on the basis of 4 different compounds: PFHXS, PFNA, GenX, and PFBS again. What I do want everyone to note is that there's 4 different compounds, 1 MCL, 3 different health effects. So if you're trying to wrap your head around some of the challenges that are going to come out of that, that's the starting point, because you've got one number that tells you risk for 4 compounds based on 3 different health effects. An example of how you calculate the hazard index is you're essentially going to develop multiple hazard quotients. So a hazard quotient is a chemical specific thing. So you take the concentration in the water, you divide it by some health-based water concentration that you developed. In this case, it's, word for word, a health advisory level, levels of contaminants at which no adverse health effects are expected to occur for even the most sensitive populations, with a margin of safety. So thinking back to those summer 2022 health advisories that we got that were extremely conservative, now we're looking at HALs for 4 different compounds, and this hazard index, you can see how it plays out, where we're at 9 ppt for PFHXS, 10 ppt for PFNA and GenX, and then for PFBS, that 2000 ppt. And so those GenX and PFBS values should look familiar because those are HALs from last year. For PFHXS and PFNA, those are from a CDC report that was published a couple of years ago. An example of how this really becomes a problem if you're starting to think through communication and working with the public on what these numbers mean. Here's an example where you have water quality characteristics that up until March probably looked pretty great. You were probably looking at those saying, I'm in a pretty good shape. I've got pretty low to no detect PFAS levels. I'm well below, the GenX health advisory level. I don't have any PFBS, and my PFHXS and PFNA are, very close to what the MRLs are. Now you're in a spot where your hazard index goes to 1.5, and so you're 50% over that MCL, and that's not something that you usually want to be at. But if you're thinking through those 3 compounds I picked up there, I picked those because they're all different health effect. So it's tough here because now you're trying to communicate 1.5 hazard index based on 3 different health effects that have, for some reason, been compounded on each other. Moving away from the standards a little bit and getting into the other requirements of the rule, we have initial monitoring requirements. So EPA 533 or 537.1 can be used. The requirement is that every system, doesn't matter if you're a consecutive system, a wholesaler, or whatever, you're measuring at your entry points to the distribution system, and you're not doing any composite sampling. The requirement is for there to be 4 consecutive water samples for the large groundwater systems and all surface water or groundwater and direct influence systems. And then if you're a smaller groundwater system, you're only having to do 2 samples at least 90 days apart. States are going to allow some previously collected data to be used from the monitoring program or UCMR5, but that's going to be at state discretion. The next item is compliance monitoring requirements. And so this is really going to look like the standard monitoring framework. So if you're reliably below the MCL, which is based on a trigger level of 1.3 ppt PFOA and PFAS, and then 0.33 hazard index, you're able to reduce your monitoring based on your system size. If you're not reliably below, you're still stuck in that quarterly sampling period with every 12 months, and you're having to continuously calculate a running annual average. If your RAA ever goes below that 1.3 or that 0.33, you can drop into reduced monitoring. But if you ever are in reduced monitoring and you get a single sample that exceeds those trigger levels, you're now back into quarterly monitoring again. So I don't know how well that's going to work out for systems to have reduced monitoring, because at these really low levels, it's easy to get a couple false positives or just get that residual ambient amount in the background that kind of comes through. The last requirements of the rule are the right to know requirements, or better known as public notification requirements. So as part of the annual reporting under the Consumer Confidence Report, all 6 PFAS that are detected above the MCLGs will have to be reported, as well as the hazard index. And then really importantly is the MCL violation. This one landed pretty much where we thought it would, which was tier 2 public notification. So within 30 days of the system learning of the violation, you have to report to the public about that MCL violation. And I believe the last item we have here is just a quick note, how to manage the waste for drinking water treatment has been a big part of the conversation. I can happily report that I think we're nearing the end of this conversation from a legislative perspective, hopefully, but essentially hazardous substance designations create liability under Superfund. That liability is extremely strict and it captures everybody. So water systems could potentially be pulled in even if EPA doesn't go after them. That'll drive up costs for drinking water residuals management. And we're hoping in the next week or two to have some legislation introduced that actually starts to drive this conversation forward, so that we get so that we start to see an exemption to that rule. So that'll be really helpful moving down the road. And I believe now it's my turn to pass it off to Katie.
All right, thank you, Chris, and good afternoon, or I guess good morning to a lot of folks on the call here. So I'll be talking today about the first steps that you should consider once you've discovered that your water has PFAS above the regulatory levels. And really, developing an action plan is likely the first step that most folks should take upon first realizing that PFAS levels are a concern. Documentation of this action plan is super important, as it will help to demonstrate to your stakeholders that you do have a plan in place, you're taking it seriously, and you want to take action. I've identified here a few key components of what an action plan might look like. So the first thing is to consider if further investigations can help with defining the source and extent of the PFAS contamination. Additional sampling, is always a good idea to consider to ensure that you have adequate data to support decision-making in the future. And then source water vulnerability assessments and PFAS source investigations are other steps to consider early on. I'll talk a little bit more about those in more detail in a little bit. Second, you'll want to determine the mitigation strategy or strategies that best suit your specific needs. So you want to consider both interim versus long-term solutions, looking at alternative sources of supplies, and potentially just making some operational or treatment changes. These are all mitigation strategies that should be considered. If PFAS treatment is a mitigation strategy that appears to be in your future, then a treatment feasibility study is an important part of an action plan. And I'll talk about this particular item in more detail in a few slides as well. So the action plan should also document any next steps, which could include pilot testing, new source development, or design of a treatment facility. And one thing that's important to keep in mind is throughout this entire process, it's really important to maintain communications with your stakeholders and start to think about how you might proceed with funding for some PFAS mitigation projects if they do appear to be in your future. So I mentioned earlier that a source water vulnerability assessment could be one component of a PFAS action plan. The goal of this type of assessment is to assess how watershed characteristics may impact PFAS contamination levels observed in your source water. So a source water vulnerability assessment may include some or all of the components listed here. I'll start with the first one there, characterization of PFAS contamination. So what this might mean is just really trying to identify any trends, doing some forensics into your water's PFAS profile, maybe looking at the carboxylic versus the sulfonic acids, comparing long chain versus short chain PFAS compounds, really just looking for some trends. The next two there, watershed transport pathways and source water evaluations should also be considered. And then gaining an understanding of the regional and historical context where your source water is located can really help to begin to understand the origination of the PFAS source. So really thinking about the sort of activities that are present in your area, looking for maybe industrial or firefighting, landfills, or military impacts. I mean, that's just a few examples of the types of activities or industries that you might want to look into and get a better understanding of what goes on in your area. It's also important to identify the historical activities that may have contributed to PFAS contamination a long time ago. These compounds are very ubiquitous. They stick around forever. So you really want to gain an understanding of some industries that maybe were a big player a long time ago that don't exist anymore. And then investigation of potential PFAS sources. So what this means is actually trying to identify a point source or maybe multiple point sources by taking a systematic approach to reviewing all of the potential sources or polluters moving upstream from your source water. So really taking a systematic approach at looking at the entire watershed that could be impacting your particular water. And then finally, the last two there, reviewing raw water intake or well construction and how that might impact PFAS levels could be important, and maybe considering some system operational impacts that could be impacting PFAS, such as well pumping rates. And then, as I mentioned before, I talk a little bit more detail about mitigation plans. So once you've gone through some of these initial steps of gathering additional data, maybe performing some additional investigations into the PFAS source, you'll then kind of want to turn your attention to developing and documenting a mitigation plan, which should be developed to meet the needs of your exact situation. But what I'm showing here are some 5 key ideas that would likely be considered as part of most anyone's mitigation plan. So first, taking a look at interim versus long-term solutions. So do you need to potentially consider some immediate PFAS remediation for your drinking water? Do you need to consider turning off sources entirely? Is there a possibility to perhaps tie into an interconnection with a neighbor right away to resolve any of the immediate needs for PFAS removal? Second, consider if operational changes could reduce PFAS impacts. An example of that is blending water sources at different ratios to try to reduce the PFAS concentrations. Third, looking into alternative water supplies, potentially, avoiding having to treat for PFAS altogether. So, that could mean a new well source, it could mean a new surface water supply, or potentially just tying into a new distribution system altogether if you happen to have some regionalization opportunities at your disposal. But really, if you've gotten to the point where you're thinking treatment is in your future, at this point, you need to focus your attention on identifying treatment alternatives. At this point, GAC, ion exchange, and RO or NF membranes are considered to be the best available technology for drinking water applications. So those should be part of this analysis. And then finally, continuing with the treatment, doing a treatment feasibility study will be super important. You want to start conceptualizing what PFAS treatment might look like for your facility at your specific site. Some things that we start to think about during a treatment feasibility study is, will pre-treatment be needed, particularly for iron and manganese? That can have a pretty big impact on PFAS removal. A treatment feasibility study should also look at a conceptual layout of equipment, a site plan, taking into consideration, specific site constraints, and very important is performing a cost-benefit analysis at this point in time as well. So now I'll just quickly go over a case study where Stantec has been working with a utility in northern Illinois called North Park Public Water District. We've been helping to develop and implement their PFAS action plan for the last couple years. So for them, this story all started back in October 2020 when they first sampled for PFAS in their well sources. At that time, all 4 of their wells showed PFAS contamination to varying degrees. Notably, PFOA was detected at levels greater than, at that time, the Illinois health-based guidance levels. And that was in each of the 4 wells. They all exceeded the health-based guidance levels. So that's really what propelled them into moving forward with developing an action plan to deal with PFAS. Actually, one of their wells, well 5, had extremely high levels of several PFAS compounds. So they decided pretty early on to just take that well offline altogether and rely on their other high-producing wells. Once North Park realized that they were likely going to need to do some significant infrastructure improvements to address the PFAS levels, they did start the SRF application process pretty quickly there. So these are all some early actions that were taken once PFAS was discovered after the first round of sampling. Then after that, Stantec helped to really develop and document their action plan, or what we call their mitigation plan for PFAS. That included several of the components I mentioned in previous slides. A high-level PFAS source investigation was performed, looking at industrial activities in the watershed. In this case, there was no smoking gun, no obvious polluter that we could point a finger to. So rather than dwell on that, it was decided that better time could kind of be spent moving forward with developing an action plan to actually address the PFAS levels in their drinking water. So a treatment feasibility study and an alternative supply study were initiated, where we looked at alternative well locations and various treatment scenarios. As a result of that treatment feasibility study, it was determined that additional land would likely be needed to support construction of a new PFAS treatment facility next to one of their existing well houses. So North Park did proceed with acquiring that additional land, which will prove to be really helpful in the future, I think. As far as next steps, at this point, we're in the middle of developing a preliminary design for a new PFAS treatment facility. That new facility is being designed to treat combined flows from their two primary well sources. Pilot testing is expected to start in the next couple of months and will be run in parallel with the design activities. During pilot testing, the plan is to evaluate the performance of both GAC and ion exchange media, and hopefully verify that pretreatment for iron and manganese is not going to be needed at this site. And also at the same time, we're doing more detailed water supply alternative study in the hopes of finding a PFAS-free alternative source that can be brought online to supplement the other well sources. The idea is they're still going to need to treat for PFAS to some extent. So moving forward with the design of the treatment facility, but also just looking for some other sources. And at this point, I think I'll hand it over to Ryan Capel, and he'll talk to you about his exciting times with pilot testing.
Thank you, Katie. I have to warn people, I have been cutting in and out during this presentation, but as you did a nice job presenting overview of what to do if you have PFAS in your water, one of the things Katie mentioned was pilot testing. And that's going to be the subject of this next segment that I'll be talking with you about. Before you go to this slide with our top 5 kind of things that we want to learn during a pilot, maybe back up. I want to introduce and build a little suspense by considering an analogy. When you go to Google and you look up the word pilot, you're not going to find a water treatment pilot skid be the first picture that pops up. It's going to be an airplane pilot. And I'd like to make an analogy that an airplane pilot is similar to a water plant operator. Think about, I've sat on the plane before watching them prepare for flights, and you look down the aisle into the cockpit and you really hope that that pilot has been through a lot of training, that they did their flight simulations, and they know what to expect when conditions change, when you have wind and weather and all these different things. You also might think about the folks that design the plane. They're hoping that the people at Boeing didn't have a glitch or something that you hear about from time to time, that they designed the plane to be able to withstand all those changing conditions. Because a pilot's job is to bring all of us passengers safely and reliably to our destination. Similar for a water plant operator, except they're not delivering passengers, they're delivering water. And we all trust that those operators are going to bring safe, reliable drinking water to us at our homes and our businesses. We also trust that the design teams that build the facilities for those operators have done their homework. And so those are some really good reasons why why a pilot study is something that we want to think about. It's like a flight simulator for drinking water. With that, we can go to the next slide. So to answer why we conduct a pilot, we've kind of boiled down 5 top reasons why we want to do a pilot, 5 things that we really want to learn from a pilot study. The first thing we want to learn about is the treatment process. What technologies are we going to be looking at? Are we looking at GAC, as Katie mentioned? There's GAC, IX, RO, NF. Maybe it's a combination of multiple different treatment technologies that works best for our water. The other thing we want to learn about in the treatment process is, will we have any complications where we need pre-treatment? I'm going to tell you about a case study and explain to you a case study in a moment where we needed pre-treatment for iron and manganese removal. Depending on the treatment process that you select, your regulators may have requirements that they require you to conduct a pilot study. It may not even be your choice. All of this is to try to nail down the right process train for your water quality. The next thing we want to learn from a pilot study is, does it work? What is the performance? So how does this perform under pressure? What's the efficacy of removal for the contaminant that we're worried about, the PFAS in this case? We want to learn about the life of that treatment technology. Is there fouling? These are all kind of interrelated, but pre-treatment, do we have fouling? We're going to also learn about residual waste. The next key thing we want to learn about is capital cost. If we do need pre-treatment, since we're on that subject, that's going to add an extra wing of a building to hold our pre-treatment equipment. That will increase our building footprint. It'll increase the cost of the project. The construction costs will go up. The next item is operational costs, media or membrane replacement. We also want to learn about, this is probably the highest contributor to operational costs, is the replacement of that PFAS treatment element. If it's a sorbent like GAC or IX, how long will it last? But of course, there's other operational costs, consumables like energy, chemicals, disposal costs. All of this rounds into item number 5, which is our overall life cycle costs. We know that hopefully we can find some funding sources, but ultimately the cost for all these improvements is going to come down and be passed along to our consumers, our customers. And so we want to learn about all of these pieces, the longevity of our design and the operational costs combined with capital costs, so that we know and can prepare our customers for what the costs are going to be. Next slide. The other thing to consider is our water, your water is unique. There's different PFAS that we've found in the water, depending on the sources. Different things can affect our treatment efficacy, like total organic carbon, hardness, mineral content, iron and manganese, like I mentioned. You might have other contaminants to deal with. All of these elements make our water treatment tricky, and that's why a pilot study is helpful. Next slide. Katie touched on these 3. We've already talked about them a little bit: GAC, ion exchange, and high pressure membranes like nanofiltration and reverse osmosis. The photo on the left is a configuration that could be either GAC or IX. It's typically a lead lag combination, where you have a lead vessel that flows onto a lag vessel as kind of a redundancy. There are all kinds of different types of GAC out there. GAC can be bituminous, subbituminous, agglomerated, reagglomerated, acid washed, coconut based. There's a lot of different types of GAC that we can test at pilot scale. Same goes for ion exchange resin. There's gel resins, macroporous resins, different resins that are being developed each day. There are folks out there working on this to improve the effectiveness of ion exchange resins at removing PFAS. Get into the high pressure membranes. We talked about nano and reverse osmosis. All right, as promised, the pilot case study I want to talk to you about is, this one took place in Cottage Grove, Minnesota. Cottage Grove is one of those epicenters for PFAS in the country, partly because it's the neighbor to the headquarters for 3M Company, where a lot of these PFAS were produced. They were disposed in the neighborhood of Cottage Grove, and they're creating issues where in 2017, when the Department of Health in Minnesota decreased health-based values, similar to the decrease that's being proposed by EPA today, we lived through this in 2017, and 8 of Cottage Grove's 11 wells were considered to be non-compliant with the announcement of that reduced health-based value. And so it prompted a few different actions. One was emergency interim treatment installations at several wells, and another was a pilot study. The first step in a pilot study is to set up your experimental plan and set up your process flow diagram. The photo diagram in the upper left is the process flow diagram that we developed with help from our folks down in Johns Hopkins University and the Bloomberg School of Public Health in Johns Hopkins, where we have an alliance with Stantec. We have equipment in a lab down there that we can use. We also have access to these best and brightest minds to help develop the best process flow diagram to fit our situation. What we had here for Cottage Grove, you'll see there's a storage tank where we took water from the wells, and then we pumped through different types of ion exchange resin and GAC. The big goal here was to compare GAC to ion exchange. So as it turned out, GAC was the first column, and then IX3 and IX4 were compared with direct flow from the well just as the flow was also going through GAC. The nifty part of the pilot study is we set up so that IX columns 1 and 2 could take the flow from the GAC as kind of a lead vessel and then flow that onto the same two ion exchange resins as a lag. So the diagram on the lower left kind of represents that lead lag situation that I was describing. Because we were curious, we wanted to test and see what would happen with GAC followed by ion exchange. This pilot study was ran 24 hours a day, 7 days a week to try to gather as much data as possible. Like I said, we had 2 trains of ion exchange resin, which back in 2020, when the study started, there were only 2 NSF approved resins. Now there are many. Then we did this GAC lead followed by IX lag. We ran the pilot for 18 months. And we learned a lot about how this works. One of the things that we learned about, speaking about pilots, we go to the next. The data here is differential pressure versus days of operation. That curve on the far left is equivalent to kind of a plane crashing, perhaps. Sometimes the best and most valuable pilots will crash. And what happened here was we found out that iron and manganese was creating a major issue on our resins, especially the yellow and blue lines represent IX3 and IX4, which are the 2 that are getting compared directly to GAC, which is the dark gray black lines. You can see GAC was affected also, but not nearly as much as the ion exchange resin. So we had to hit timeout and restart our pilot. Like I said, a very valuable lesson. It cost us thousands to run this pilot, but this was $1 million discovery that we needed to put pretreatment into our full-scale design. So we did that. We put in a berm media, which is a manganese dioxide coated media, and things ran smoothly as we would have expected. Eventually, that media did start to break down. You can see that the differential pressure started to climb again. We took the pilot down and replaced with a different type of media. This was a Philox media. So we're starting to learn a little bit about the pretreatment, and away we go. Things were much more smooth until that media started to break down as well. Interestingly enough, this is just showing you differential pressure. The PFAS removal the efficacy of removal was high for all of these treatment combinations. So even though we were seeing differential pressure, we were still removing PFAS. The problem is that if we hit a differential pressure of 20 PSI, that's what the manufacturers of the contactors say is the maximum level that you want to hit. So we were going to have a situation where without pretreatment, iron and manganese was going to shorten the life of our PFAS treatment. So we needed to put in pretreatment. The next slide is going to show you about efficacy, trying to hit on those top 5 things that we want to learn about. Number 2 on my list was efficacy of treatment. So what you're seeing here, there's a lot going on. We don't have time to break it all down, but what you're seeing are breakthrough curves with concentration versus bed volumes on the x-axis of each of those 5 columns that I mentioned. GAC is on the left, IX1, 2, 3, and 4. One of the things you're seeing here with the breakthrough, the flatter the breakthrough curve is, the better it's performing, the less of our PFAS is breaking through the treatment sorbent. So what you'll notice right away, and I want to point out with this time we have, is that this is evaluating 12 different PFAS substances. 6 of those are carboxylic acids, the ones that end in an A, and 6 of them are sulfonic acids, those substances where the acronym ends in an S. The upper half of these graphs are the carboxylics. The lower half are the sulfonic acids. The thing you'll notice is the curves that involve ion exchange resin are much flatter on the bottom half of this chart. It's because they are doing a better job at removing sulfonic acids than the GAC is. If you look at the left-hand side, lower left, that is the breakthrough curves for GAC compared to all those IX1 through 4 are much, much flatter. So if you have a water quality that contains more sulfonic acids, ion exchange resin is looking like the better choice for you. You will notice that IX1 and 2, and recall, those were we'd expect those curves to be flatter because that was a dual treatment, a lead lag scenario. All right, so all of this pilot testing and gathering of data is to inform us about a full-scale treatment design. We want to build the best airplane for our water plant operators to fly. It's to give them the best chance to deliver safe, reliable drinking water. So on the next slide, we go through all the lessons that we learned, and they kind of touch on those top 5 things we want to learn about. 1, what was the treatment process that we're going to use? We checked ion exchange resin and found that it met the muster as a viable alternative GAC to GAC for removal of PFAS. With the limited time we had in the pilot, with 18 months and the lead lag scenario, we did find that GAC followed by Axe was an even better alternative, but we need more time to really see how that would play out, seeing as it was a dual treatment. We learned that dissolved oxygen had an impact and could potentially be an issue if you have a holding tank in between your treatment process. So we're learning about the order of that treatment train. We learned that you don't likely want to have a holding tank in between, and you do want to have some pre-treatment for iron and manganese. Very valuable lesson learned there. Indirectly, we learned, you can see in the photo on the right that there's some clear columns. Biological growth can occur if you're a surface water and you happen to have your treatment process outside. If there's GAC involved, biological growth could be a contributing factor you'd want to test in a pilot study. Finally, I just wanted to inform that, and if we have
We might have lost Ryan there. I'm going to go to the next slide. And Kim, you can take over.
All right. Yeah. And I think the last note Ryan was just making there was that those results are going to be published soon in a journal for everyone to review. So yeah, so moving on to some funding considerations, both Katie and Chris have started to hint at this. We have to find ways to pay for all of this very important work that needs to get done. So there's lots of different ways, as we all know, to fund water infrastructure and operations. The majority of costs are typically recovered through user fee revenue. But you can also, some utilities can levy tax revenue. Some can access and leverage private financing. Bonds can also be issued to allow and be repaid using your user fees, so that those costs can be spread over multiple years. Specific to PFAS, settlements can also come into play. And then earmarks were reintroduced starting 2 years ago. So talk to your representatives. Right around now is the time that they're putting together their final earmark requests. And then finally, there's a large influx of grants and subsidized loans coming from the feds and from the states. So this last one is what we wanted to discuss today, because federal grants historically have funded for around 40% of capital infrastructure spending. And so because of that, we wanted to highlight 3 federal grant and loan programs for PFAS in drinking water. All 3 of those are coming from the EPA. And they are provided as formula allocations to states, which states do have to demonstrate need for and apply for every year. And then the states distribute those funds within their state level funding programs. So these are the 3. First, the EPA has a new program created by the Bipartisan Infrastructure Law, the Emerging Contaminants in Small or Disadvantaged Communities program. 100% of the $1 billion in annual funding through this program will be made available as grants to disadvantaged communities or small communities with less than 10,000 people population. Disadvantaged communities is defined by the states. The second program is the Emerging Contaminants Set Aside within the Drinking Water State Revolving Fund. This will have $800 million in annual funding that's offered as grants or subsidized loans with principal forgiveness. And per the legislative text, 1/4 of these funds must go to disadvantaged communities or small communities, which here is defined as less than 25,000. But I will also note that this program is a Justice 40 covered program. Justice 40 was an executive order that requires certain programs to have at least 40% of benefits going to disadvantaged communities. So that's an inconsistency. The EPA hasn't yet released how they're going to settle that, but could be up to 40% there. And then finally, there's the normal SRF program. So I'm referring to it here as the infrastructure account, and this is not PFAS or emerging contaminants specific, but just for drinking water as infrastructure as a whole. But it has a base appropriation of $500 million annually. And through the bipartisan infrastructure law, it did receive additional funds of around $2 billion per year. 49% of these funds must go to disadvantaged communities, and those are available as subsidized loan with principal forgiveness as an option as defined by the states. So, as many of you may be wondering, what activities are actually eligible under these 3 different programs that we're highlighting? And I want to note that the primary purpose of any funded project must be to address emerging contaminants, which has been defined as around or at least 50% of the cost or level of effort of the project going to emerging contaminants. I'll also note that these eligible activities outlined in this table are based on initial guidance and implementation plans from the EPA. None of these were actually specified in the authorizing legislation. This list has been developed by the EPA, but it's still subject to change. So it may be up to individual states to decide how they spend their allocations. So the first fund, this is the one for small and disadvantaged communities. It can fund the entire project lifecycle. So investigations, like Katie was talking about, pre-project planning and design, some of those piloting efforts that Ryan was talking about, the construction, obviously, implementing the project, and then some technical assistance as well. But this fund isn't available, or this fund is available just to small and disadvantaged communities. So if you're not small and not disadvantaged, the second and third programs would be an option for you. So the second program, the Drinking Water SRF and the Emerging Contaminants Set Aside, this can fund those initial investigations and bring the project all the way up through design, but can't actually fund the construction itself. But it does offer technical assistance to support an SRF loan application for the infrastructure dollars to then construct the project. The Drinking Water SRF infrastructure account can't fund those initial investigations, but it can, after some project conceptualization has been done, can start funding the planning, design, all the way through construction. And if you're interested in any of these funds, we'd really recommend requesting a scoping call or just reaching out to your state's SRF program administrators. Each state gets to define disadvantaged communities. They get to determine eligibility for these funds. They get to set priorities for these funds. So they're really going to be your best resource for these. I'll pass it back to Nicole to close us out.
All right, thank you, Kim. So just some quick webinar takeaways. As we know, the draft MCL was published on March 14th of this year. And if your PFAS levels are above these proposed regulatory levels, we recommend that you start developing an action plan. Consider piloting because it should help you minimize your costs, particularly life cycle costs, and optimize the treatment that you're using. And know that there is funding available from federal and state sources, and Stantec can help you with all these items. We very much appreciate your participation today. And at this point, we are happy to answer some questions. And Heather, I think you're going to facilitate that.
Thanks, everyone. Great topic today. So we've had a number of questions rolling in, so we'll get started with those. First question, do the PFAS within household products, floss, nonstick pans, etc., pose direct health effects? How does the exposure, delivery mechanisms via drinking water ingestion pose the health effects? If the former, is there legislation being considered to address the manufacturing / distribution of these compounds? Nicole, could you please answer that for us?
Yeah, so I'll take a first shot at it, and then if Chris is there, I'd love to have Chris comment on this because I'm definitely not a toxicity of PFAS expert, but yes, I do believe that the PFAS from household products can cause a toxicity issue in humans. As I understand it, EPA has kind of deemed that water makes up about 30% of the health impact of PFAS to people, and they have a 300-page report that I kind of tried to digest. on the toxicity assessment that they did as in association with this maximum contaminant level draft regulation. And so you can find that on their website if you really want to learn more about toxicity of PFAS. But PFOA and PFAS, as I understand it, were essentially regulated in the 2000s era, so that they are no longer manufactured. But there's all these other compounds that have been substitutes like Gen X that are still out there. And because PFOA and PFAS are just so ubiquitous and they hang around in the environment, we're just still seeing them in our source waters. Chris, do you want to add anything to that?
Sure, I have a couple little comments on that too. So the one thing you just mentioned was that PFOA and PFAS were kind of regulated in the 2000s. So the caveat I'd put on that is EPA did some voluntary phase out with 5 or 6 or maybe 8 of the main manufacturers of PFOA and PFAS. You can probably name the 8 if you wanted to try, but they're still, in theory, they could still be manufactured in the country, and they're certainly still used commercially. So there's still ongoing sources. We still have AFFF stockpiles that are being used that have PFOA and PFAS in them. And then there's all these other things. So they've still not really been regulated or banned. For the exposure to different PFAS based on different routes, I think toxicity is from exposure. So once it makes its way into the body, it does generally show the same type of toxicity for PFAS at least. So if your body uptakes it from a cooking pan that has PFOA and it leaches from the pan into the food and you ingest that, you're still going to have exposure just like you would in drinking water. The challenge for EPA right now is that they don't have adequate data on those other sources yet. They've focused so much on drinking water, and mainly that's why I tried to frame that up earlier today too, is that all the focus has been on drinking water, and they really haven't started to look at sources industrially, other products, and there's a lot more state legislation getting to those issues than there is federal, but federal legislation, I think every year we've had something introduced that hits on banning PFAS products, banning PFAS in this, so we could eventually see it, but right now it's primarily a state level legislative effort.
Great. Thanks, Chris. Thanks, Nicole. What are the treatment scheme for the reject of RO/IX for PFAS? Katie, could you respond to that one for us, please?
Yeah, sure. That's a great question. I'll start with the ion exchange, and I'll kind of add on to that GAC. So with PFAS treatment with GAC or ion exchange, the normal standard operating protocol will not have regular backwashes occurring, but backwash might be required at some point in time, either to improve operations or when you're replacing the media, you'll need to do sort of like a backwash procedure. So there will be a waste product that comes from the GAC or the ion exchange PFAS treatment scheme that will obviously need to be handled in some way. And if it is believed to have PFAS contamination in it, there's obviously a lot of uncertainty with how to deal with that disposal, because some of the more traditional paths for disposing of waste like backwash waste would be to a sewer perhaps, or in some parts of the country, maybe evaporation ponds, depot injection, and these will all become potentially more risky. Definitely some questions will arise as the regulations continue to develop, which Chris talked to a little bit with regards to CERCLA and everything. Everyone's going to be taking on more and more risk with disposal of PFAS waste streams from drinking water treatment plants. The RO reject is a great question. With RO, there will be a concentrate disposal stream, and it will be a major challenge. With the RO disposal stream, it will be low volume, high concentration of PFAS waste, which you can just use GAC or ion exchange as a way to treat that stream, which can be really effective. And then just thinking about the future and some like innovative approaches, because this is a low volume and high concentrate waste stream, perhaps some of these destruction technologies that the super smart folks out there are working on could become useful. Right now, these destruction technologies for PFAS that are being worked on aren't super applicable to the main drinking water treatment stream because it tends to be high flows, low concentrations. But with the low flows, high concentrations, I think, or I guess we all hope that the destruction technologies will be able to maybe provide some answers in that area. I don't know, Chris, if you have any thoughts on the risks and future of disposal of PFAS waste, that might be nice to chime in.
Yeah, I mean, I think you kind of characterize it up well, but I mean, primarily there's two big actions that are going to put a lot of hurdles in the way for destruction and disposal techniques down the road. The first one is the circle you already mentioned, and that's really because that liability is going to come in, and then there's going to be all these questions, like you said, about, okay, so you start up a PFAS treatment system, you do backwash, you put all that backwash into an evaporation pond, and somehow it leaches into the drinking water or the groundwater and goes downstream to a Superfund site. Are you now liable? How much are you liable? Who could pull you in? All those questions come in. The other big action that I didn't mention that is coming up this summer is they're planning on moving forward with the Resource Conservation and Recovery Act, which is more about the hazardous waste side of the conversation, so how you manage waste actively. I don't know how that will play out with drinking water yet, but it's kind of a stepping stone to a hazardous waste designation for PFAS. So that could potentially have some serious issues because we have all these treatment products that concentrate and create high, at least higher than PPT concentrations of PFAS. So that's something else to watch out for.
Thank you both. Next question in, iron and manganese were briefly mentioned with respect to PFAS treatment. What are the concerns and considerations for iron and manganese? Ryan, could you take a shot at that for us?
Yeah, thank you. Good question. I tried to touch on, for what we experienced in Cottage Grove in that pilot study, the iron and manganese concern wasn't so much about how it affected PFAS removal and efficacy of PFAS removal. It was just that it did tend to complex or create differential pressure, particularly on the ion exchange resin. So it would stick preferentially to the surfaces of those ion exchange resins, which would create kind of a differential pressure barrier on top of the column. And so then that's where we saw those differential spikes. And so even though that the iron and manganese was building up on the surface lens of that ion exchange resin, it wasn't negatively impacting the PFAS removal. So it's mostly just all about extending the life so that we don't have differential pressure spikes that go greater than what the equipment manufacturers recommend at 20 PSI. Does that answer the question, I think?
I think so. I'll wait for additional question to come into the queue. Okay, another question for you, Ryan. Can you please advise what EPA testing method is used by the labs to detect PFOS? What we have seen available, the MDL, is to PPT.
Yeah, I don't know if Joe is still on the line. It'd be nice to hear from Joe Jackangelo. He is our connection to Johns Hopkins University and could probably answer this one. If he's not, I can take a stab at it. We do have the standard methods of testing, the 533, 537 EPA methods, which Johns Hopkins lab is capable of conducting. The Johns Hopkins folks, it's not a certified lab, it's academic lab, but we were able to utilize those folks to conduct all of the analytical testing for our pilot study. Hundreds of tests were taken throughout the course of that 18 months. And the turnaround time, I did want to mention this, was only 4 days. So I'm getting away from the question a bit, but
Hey, Ryan, I think you just
4-day turnaround, 4 weeks.
Let's see if we can get Joe. You there, Joe?
Okay.
Yeah, I'm here. Yeah, I mean, well, just my 2 cents in here is that, yeah, you could get an MDL around 2 ppt. And that's not unusual for sophisticated laboratories to be able to do. To get an MDL about 2 ppt, and I'm going to generalize here, is that your detection has to be about 0.5 nanograms per liter. And then when you statistically determine the MDL, you get up around 2 ppt. But of course, the limit is or the regulation is around 4. I think the issue comes around what Chris had mentioned, getting down to, I think it was 1.3 for reduced monitoring or for other action that needs to be taken. And so as a result, you'd have to, that's very difficult, getting down to that level. But most analytical labs, the detection level for many, not all, but for many are around 0.5, certainly not more than 1.0. So 2 ppt is that you saw, not unusual at all.
Great. Thanks, Joe. Okay, and we are at the hour. So with that, we're going to wrap it up today. Thank you all for your participation. If you have any other questions for the panel, please direct them to Nicole Boulay. Her contact info is in the chat. You'll receive an email within the next week with your participation certificate. We will also be posting this presentation on stantec.com if you'd like to listen again or share with a colleague. Our next presentation will be on Wednesday, May 17th, where our panel will be talking about EPA's latest proposed modifications to the steam electric generation effluent limitations and guidelines. Hear about the proposed changes, areas that industry may want to comment on, and how these proposals may impact the future of coal-fired power plants. We look forward to you joining us again soon. Thanks, everyone.
Thank you.